So right here I have a cubic function, and we are going to use the integer root theorem to find its zeros. So the integer root theorem is very similar to synthetic division, but it can be used for higher degree functions as well, where none of the x-intercepts are known or given. So essentially it claims that the possibilities of x-intercepts for a function come from the factors of its constant, considering each of these factors possibly positive or negative. And remember that the number of x-intercepts of a function is equal to its highest degree. So right here, because I have a cubic function, the amount of zeros that we're trying to find are 3. So the first thing that we're going to do for the integer root theorem is find all of the factors of the constant, since these are the possibilities of x-intercepts for this function. So 80. So we have 1, 2, 4, 5, 8, 10, 16, 20, 40, and 80. So these are all of the possibilities of x-intercepts for this function. Now, because these are only possibilities, they're not actually all true roots of the function. So to be able to go any further with the integer root theorem, we have to find at least one root so that we can find the rest. So to find one of the roots, we're simply going to plug in each of these values into the function as x, each of them positive and negative, until we find one of them that makes the function equal 0. And you can do this in the calculator. You don't have to do it by hand. As you can see, I started plugging in each of these factors, both positive and negative, into the function. So I did positive 1, that did not equal 0. I moved on to negative 1, also didn't equal 0. I moved on to 2, didn't equal 0, and then negative 2 finally equaled 0. This can be a bit of a tedious process, but it's kind of the only way that you can do this. So until you find a factor that makes the function equal 0, and in this case, we have negative 2. Now that we have one of the actual roots, so we can already write down that x equals negative 2, because that is one of the actual x-intercepts for this function, we can now find the rest because we can use synthetic division. Since synthetic division is precisely used to find the rest of the x-intercepts once you have one known. And now that we have one that's known, we can simply use it. We put the root, and then we write the coefficients, and then we do So now we have a quadratic function. And a quadratic function, if we solve for its x's, are going to give us 2 roots. And we already have one here. So in total, we're going to have 3, which is precisely the degree of the function. So we would have found all of the x-intercepts. So now all we have to do is literally solve for this quadratic equation. Now, we can try to factorize this. So in this case, we would have to use the star method. We do 40 times 320, negative 120, and then negative 7. So we can do negative 15 plus 8. Since that's going to give us negative 7, there's some, but multiplication is going to give us 120. So then 3 over negative 15 can be simplified to this, and 3 over 8 can't be simplified. It's just going to be that. So then the factors are going to be now x minus 5, and 3x plus 8 equals 0. So x equals 5, and negative 8 over 3. So then we just add this to the other ones we had. boom, those are the x-intercepts for this function. Voila! So all you do is, first of all, to recap, you find all of the factors of the constant, and you have to consider each of these positive and negative. You plug each of these in. You can do this into the calculator until the function equals 0. Whichever one makes the function equal 0 is one of the actual roots for the function. You use this root in synthetic division to get a function with 1 degree less than the original one. In this case, we got a quadratic function, so then we just solve for it, and we're going to get 2 factors. We turn them into roots, and we just add it to these ones. If you're solving the x-intercepts for functions that are greater than cubic, for example, quartic, quintic, or even above that, you would still use the same procedure, but when you use synthetic division, instead of getting a quadratic function, you're going to get a function of 1 degree less. So for example, if you're having a quartic function, you're going to get from synthetic division a cubic, and then you're going to do the same thing. With that cubic, you're going to find the factors of that constant, of its constant, and then you're going to plug them in until you get 0, use synthetic division for that, then you'll get a quadratic, and then you'll solve. If you did a quintic function, you would do the same thing, but synthetic division is going to give you quartic, then you would find the factors of its constant until one of them equals 0, then you'd use synthetic division, you'd get a cubic one, then you would do the same thing until eventually you get to a quadratic function, and then you can solve it. So it's the same procedure, you just have to get to a quadratic.